Okay, so welcome back. Let me kind of go back and say where we are at this point. Okay, so where we are, or where we were pre-midterm. Okay, so we had a matrix inducing a linear transformation, if you would like, going from Fn to Fm. And then we saw that we could put A into reduced echelon form. So maybe reduced row echelon form. So the most important thing about this form, or the most important thing to look for, was that there were these entries called pivots. Okay, let me just do an example here. Okay, so these were entries of the matrix with that were ones. Okay, so these pivots were ones with zeros above and below. Okay, and you use these pivots to cancel out terms in the previous rows, so you get these zeros. Okay, and they told you kind of the qualitative behavior of what the matrix did. Okay, so in particular, as a linear transformation or as a matrix, this AX equals 0 had a unique solution. If and only if there was a pivot in every column. Okay, I want to say that AX equals B has a solution if and only if there's a pivot in every row. It's not exactly true, but it's if and only if the reduced form does not have a row of all zeros, and then a non-zero term here. Okay, so has a solution if and only if this does not occur in the form. Okay, so today we're going to make this a little more quantitative in the sense that we're going to care about the size of the set of solutions. So we want to know exactly how many x there are, which is equal to 0. We'd like to know the size of the image of A under this linear transformation. Okay. So first, let me just give you kind of a theorem, which is a general solution to the equation AX equals B. Okay, so here A is a matrix. Maybe I should say A goes from F to the N to F to the M. So X is here, B is here. Okay. Of course, there might not be a solution, right, if the image of A does not equal B. Okay, but the theorem is once you have a solution, okay, so let x1 satisfy this equation. Okay, so in the sense that ax1 is equal to b, and let h be the solution set of ax equals 0, okay, then the way that you get the set of solutions, I'll say the set of solutions to ax equals b is of the form, well, you take a sum, x is x1 plus xh, where x1 is the vector that you're given, and xh is in h. Okay? So in other words, the way that you find the general solution is, well, first you find the solution to ax equals 0, and then tack on something which sends you to b. Okay, so maybe I'll just add a remark here. So an equation of the form ax equals 0 is a homogeneous equation. Okay, and in some sense this is saying you can restrict yourself to finding solution sets of these equations. The way that you find the solution in the general case is just tack on one thing that that hits your image vector, okay, if that exists, okay? Okay, so the proof is pretty simple, okay? Again, it kind of moves the difficulty into figuring out the solution set here, okay? But once you have that, so we're just going to show double containment here of the set of solutions versus the set of sums, okay? So, well, first, if you're here, oops, and I guess, sorry, this should be this way. Suppose x is of the form x1 plus xh, okay, for xh and h, x1 is above. Well, then a of x is equal to a of x1 plus xh. So this is a of x1 plus a of xh. So this is b plus 0. Okay? So if you're of a sum of this form, you certainly are going to map to b under a. Okay? On the other hand, suppose you have a solution. Okay, suppose ax is equal to b. Okay, so x is a solution of what we want. We also have, we're given that ax1 is equal to b by assumption. Okay, then I claim that x1 minus x is in h. Okay, so this is just because if I look at a of x1 minus x, I get b minus b, so this is 0. Okay, so therefore, well, x is just equal to x1 plus x1 minus x. This is in h. This is a solution. Okay, goes to b under a, so that's the proof. Okay, so this is a very nice general theorem. Maybe I'll add another remark. We don't even need a finite basis for this to be true. Okay, this is a general statement for vector spaces and linear transformations. Okay. On the other hand, as I said, what you really want to do now is study the solution set of ax equaling 0, right? Once you've figured out that, you've figured out everything, but of course we still want to figure out what that is. Okay, so this is important enough to have its own name. Okay, so let me just say I want to think now just going from V to W, vector spaces. We're going to say that the kernel of A is the V in V, where AV is equal to 0, so exactly that solution set. I will probably shorten this to kernel A, okay? And then so I'm going to use this notation in the book, which I kind of despise. So they say the range of A is the image, okay? So W is AV. And they say ran A to be this set, okay? So I would greatly prefer something like this, but I'm going to stick with the book's notation. Okay, mainly out of laziness, but also not wanting to have people get too confused about the notation. All right, so let me just make a note here. These are both vector subspaces. Subspaces of V and W respectively. Okay, so the picture here is that we have V, A maps it over into W. Let's just say it's going from R3 to R2. It doesn't have to be surjective map, so this might be the range of A here, and the kernel of A might be some plane here. Okay, obviously there's different choices and you'll get different dimensional subspaces, but this is some sort of general picture. Okay, so let me note here, if we have A as a matrix, okay, so let's suppose if you want that this is just going from Fn to Fm, Then we have the transpose of A, which will also be useful to keep track of. Okay, so the transpose is a map going in the other direction. Okay, from Fn to Fm. And what we will be interested in is, so we're going to be interested in these four subspaces. Okay, so kernel A, range of A, kernel A transpose, and range of A transpose. Okay, so it will also be useful to keep in mind what's going on when you're putting A or A transpose into reduced echelon form. Okay, so let me just add these to the picture here. Okay, I'm going to zoom out a little bit. So we have matrices here, which are invertible matrices going from Fm to Fm. So these were our elementary matrices. And what these do over here is, well, they're row operations on A, okay, putting A into echelon form. Okay, so in other words, when you're doing these row operations, you're over in your range, changing the basis of the subspace so that A has a nice form. Okay, on the other hand, you can work over here and do row operations for the transpose, which are the same, I guess, as column operations for A, okay? But again, over here, you're going to change the basis, so A transpose has a nice form, all right? So let me give you one more key definition before, well, I'm going to give, I guess, a couple. So the first is that the rank of A is just the dimension of the range of A. Okay, or the image. All right, so in other words, you're just taking the dimension of this subspace. Okay, so the next definition is one that we're actually going to see later in the course. Okay, so I'm not going to go into full details at all now. But I think it's a natural question, you know, if I give you this map A to an A transpose, you know, what kind of relation do these maps have, right? They're not inverses of each other. Or certainly they're not always inverses, okay, but what relation do they have? All right, so the book doesn't really say this at this point, but I'll just slip in something which will give you some hint as to what's going on. Okay, so I think I'm just going to I have to work in f to the n, and actually this has to be r or c, okay? So two vectors, v and w, are orthogonal or perpendicular. Okay, so we write v perpendicular to w if the quantity v1 w1 plus v2 w2 up through vn wn is equal to 0. Okay? So in other words, if you think of the v sub i's as a 1 by n matrix and the w sub i's as a n by 1, okay, then this product, like the matrix multiplication, is 0. Okay, so again, I won't go into all the details, but it turns out that your intuition for what perpendicular means will work with this definition. Okay, so you can check, for example, that the elements 0, 1 and 1, 0 are orthogonal. Okay, we think of them as being perpendicular, as having 90 degrees, or you can look at 1, 1 and minus 1, 1. And it turns out that, well, when we put a bit more structure on our vector spaces so that we can do some geometry and measure angles between vectors, then this will exactly correspond to them being 90 degrees. Okay, so let me, before justifying why I'm introducing this definition, kind of randomly, let me say first that if V is perpendicular to Wi, okay, for say some collection of vectors W1, W2 up through Wk, okay, then V is perpendicular to a linear combination. Okay, so alpha 1 W1 up through alpha k Wk. So in other words, you take any a vector in the subspace generated by the W sub i's, and if V is orthogonal to all of them, it'll be orthogonal to every vector in that subspace. So if you'd like, I mean, it follows immediately from the definition and expanding things out. If you want, you can think, if you put a linear combination of vectors here and then apply this as a linear transformation, well, if you're getting 0 for every vector, this linear transformation will give you 0 for the sum. Okay? So another thing that's going to be useful here is that if you're perpendicular, let's just say you're perpendicular again for some collection of vectors, okay, then in particular, you are not going to be in the linear combination. Okay, so if you're perpendicular, you can't be equal. So V is not in the span of alpha 1 W1 up through alpha k Wk. Okay, so why is that? Well, if it were true, then you would have V is perpendicular to V, which we should check in the definition that this does not occur. Okay, so this would be the V1's V1 plus V2 V2 up through Vn is equal to 0, and this is now a sum of squares. Oh, so I should say it's not perpendicular to V unless it's 0. Okay, so this is a contradiction unless all the VI's are 0. Okay. So notice this is, I say it like it's nothing, but of course this is not true for something like the field on 2 elements. Okay, so it's not true here. And I think this is the reason really why the book doesn't mention it now. It says you really have to be careful about what field you use. Okay, if we're doing RRC, everything is nice though. Okay, so now let me justify why I'm introducing this concept. Okay, so why perpendicularity, or why orthogonality? Well, let's suppose X is in the kernel of A. Okay, so I guess I'll just draw the picture again. Maybe I'll make it 2-dimensional this time. So we have A. Here's our kernel. Here's our element X. Okay? And now we'd like to know something about the transpose, what this looks like. Okay? Well, in this case, I mean, in general, we can say that X, so in this case, X is perpendicular to W for any W in the transpose, of the image of the transpose. Okay? And sometimes we just say X is perpendicular to the image of this map. So you're perpendicular to subspace if you're perpendicular to each vector in that subspace. Okay, so what we know is that if this is the kernel, the image, see, I have to use image of a transpose, it's too natural. The image is going to be orthogonal to the kernel of A. Okay, so why is that? Well, I'll just write down A. Okay, so it'll be general form A1, alpha 1, 1, alpha 1, n, alpha m1, alpha n, mn. Okay? And we're mapping in x1 up through xn we're saying this is 0, right? This is x is in the kernel of A. So in other words, we have alpha 1, 1, x1 up through alpha 1n xn is equal to 0. I'll just write one more. Alpha 2, 1 x1 up through alpha 2n xn is equal to 0, all the way up through alpha m1 up through mn xn is equal to 0. Okay? So this is just this, the system of equations that you get from being in the kernel of this matrix. Okay? But notice what each of these equations is saying. It's saying that for each row of A is orthogonal to this vector xi, or to the vector x. Okay, so each row of A is orthogonal to x. Okay. On the other hand, this means that the column of A transpose is orthogonal to x, but the column of A transpose is just the image of standard basis vector for Fm in Fn. Okay? So in other words, what you have is a vector x. It's in the kernel. Okay, so it gets sent to 0. Now, this means that it satisfies this equation, and that means that the entire image of A transpose has to be orthogonal to it. Okay, so we have A here, A transpose. Okay, so this is a very useful picture to keep in your head. Maybe I should say in some cases it doesn't tell you too much. All right, so if A has no kernel, then you don't get any information, okay? It doesn't mean that A transpose has no kernel. A transpose might, right? All this equation is telling you is that the image of A transpose is orthogonal to the 0 vector. But everything's orthogonal to the 0 vector, so you don't really gain any information. Another thing to just keep track of is that the image of A transpose may not contain every orthogonal vector to x. Okay. So in other words, I have this vector x. I can look at all vectors that are orthogonal to it. I know the image of A transpose gets sent into there, but in general, you don't really have any control of how large the image of the subspace is. Well, it turns out you will have some control, but it might not be everything. Of course, you can also apply the same logic to the A transpose map, right? So if I take a vector here, y, which is in the kernel of A transpose, well, then you know something about the image, right? So now you can work out the image of A has to be orthogonal to y. Okay? All right, so that is the picture to have in mind, I think, for what the transpose map does. So let me go back to echelon form now. Okay, because now this should tell us something about the dimension of these 4 subspaces that we're interested in, right? So let me just remember here, we want to understand the kernel of A, range, kernel A transpose, range of A transpose. Okay? Okay, so now we have a matrix A, which is perhaps not an echelon form, and it's echelon form, which I'll call AE, okay, to mirror the book's notation. Okay, so to find a basis for the kernel, I'll start here. So to find a basis for kernel A, well, essentially we just have to solve ax equaling 0 using the reduced form. Okay, so there's no great trick here. So let me give you an example of how you might obtain a basis from solving the system of equations. It will depend on the free variables used. So let me say we have x2, x3, and x4, and we figured out that the solution to ax equals 0 is x2 plus 3x4, x2 minus x2 minus 5, x4, x4. Something like this, okay? And you can work out easily the reduced echelon form that will produce this solution, okay? So what you get from this is that every solution is of the form x2 times, let's see, 1, 1 minus 1, 0, plus x4, 3, 0, negative 5, 1. Okay? So every time you've kind of written down a formula for the equations in terms of certain free variables, you've now found a basis. Okay? So every solution set will be some linear combination of these two vectors. Okay, so you found a basis out of many, I should say, right? There's many possible, of course, bases for the kernel, but you can always obtain them by looking at the coefficients in front of your free variables in a solution. Okay? Of course, you still have to go through the work of solving it. That's just life. Okay? Let's find, so that's the kernel of A. To find a basis for the range of A, okay, you use, this is actually easier, you use the columns in A corresponding to the pivot columns in the reduced form. Okay? So in other words, you take your original matrix A, okay? Remember, the image of any of the basis of the standard basis vectors correspond to the image of the columns. So that makes sense that these would give you a basis. But of course, it might not be an injective map. These, or in other words, these things might not be linearly independent. And the failure of linear independence is exactly encapsulated in the fact that some of these columns don't have pivots in them. So this is going to go to something like this, and so on, okay? And then you look at the columns that have pivots here, look at the corresponding columns here, okay, and that will give you a basis. Okay, so the book provides a pretty detailed reason for why this is. I'm not going to give the full reason, I'll just draw the geometric picture of what's going on. So we have A going from R3 to R3. Its image, say, is contained in a lower dimensional plane. Okay, well, then you have three standard basis vectors here. Under A, they'll go to three vectors, which are now spanning a plane. Okay, so there's going to be some linear relations between them. The entries of A are exactly these images, and when you find out which columns have pivots, you're exactly, and then choosing those, you're exactly choosing a subset of the vectors which is linearly independent and still spans the image. Okay, so you can check that the pivot columns still span, okay, still span the image of A. You can notice this here, for example, if this second column is redundant, since I've already captured that vector in the first column. So the pivot columns still span the image. and you have to use the original matrix, okay, but those still span the image and are now linearly independent. Okay, so you can just read this off the form. Okay, so that is the image and range of A. Now I could just say you can do the same thing for A transpose. So for the kernel of A transpose, this is just what you do. You have to solve A transpose of x is 0. Again, if you've worked out the image of A, then you know that the kernel of A transpose is orthogonal to all vectors in the image. Of course, that still might might not be the entire orthogonal complement, so you just have to solve for it. Okay, and for the range of A transpose, you get lucky in a sense that the pivot form, so the pivot rows of the echelon form. Okay, so this is in the form for A, not in the original matrix, but now in the new form, give a basis for the image of A transpose. Okay, so let's see why this is. Again, the book has a very detailed explanation, and I'll give a more heuristic one. Okay, so first note that we should be looking at the rows. Okay, so first note that the range of the transpose is certainly spanned by the rows of A. Okay? Because this is just the rows of A correspond to the images of standard basis vectors under the transpose map. Okay? So certainly we have, if we're looking at the rows of A, that's a good place to start. Now when we do row operations, on A, what does that correspond to? This corresponds to changing the basis in the range of A, right? Okay, so when we have a matrix A, and we put it into reduced form, usual picture looks like that, okay? All that we've been doing is the way that we've gotten from this form to this form was by a nice choice of basis for, say, f to the m. I think that was my domain of A transpose. So in other words, these row operations do not change the image of A transpose. All right? If I give you a linear transformation between two vector spaces, and then I write in some matrix, and then I change the basis of the domain, I get a different matrix, but the image is exactly the same. Okay? So when I'm doing row operations for A, okay, all I've been doing is doing a change of basis on the domain of A transpose. Okay? And what that corresponds to is, well, it doesn't change the image. You've just made the image of the vectors that transpose nicer. Okay, so the pivot, I'll just say the rows of the reduced echelon form still span the range of A. The range of A transpose. Okay, you haven't changed what the range is at all, just written them in nicer form. And choosing the pivot rows gives a linearly independent set. Okay, and that's for the same reason as choosing the pivot columns. For A, if you have rows with no pivots in them, those are going to be spanned by the subset of vectors of rows that do have pivots in them. Okay, so it gives linearly independent and hence a basis. Okay, so now we've done some work. We're going to now get to state some theorems with trivial proofs, okay, but they're going to be important for us to work with in the future. Okay, so here's the first theorem. It's called the rank theorem. And what it says is for a matrix A, the rank of A is equal to the rank of A transpose. Okay? This is now the proof is trivial because we can just say number of pivot rows, which is the rank of A transpose, is the rank is the number of pivot columns. Okay, which is the dimension of A, or rank of A. Okay, so that's a nice theorem. I mean, in my perspective, it's kind of surprising in some sense that A and A transpose have such a relationship. Another theorem is A is again matrix. We can now combine more of our subspaces or more relations. Let's say A is as a transformation, it goes from Fn to Fm. Okay, so the first thing is that the dimension of the kernel of A plus the dimension of the range of A, so the rank of A, is n. Okay? So the other theorem is essentially the same thing for its transpose, but we can say the dimension of the kernel of A transpose plus the dimension of the range of A transpose is m. On the other hand, this is also just the dimension of the rank of A, or the range of A. Right? So these are equal. But now we have, since A transpose has domain M, we get these relations. Okay, so I'd like to, we've done a lot of work to get this theorem, so I want to give some applications of it. Let me give you a corollary, okay, which says that if n is equal to m, so if A goes from, I'll just say from V to W, so maybe I should say the same exact thing works in general, okay, for any two vector spaces. V and W are the same dimension, and if the kernel of A is 0, I'll just say it this way, A is surjective. Okay? So this is kind of a nice way to check if you have a linear transformation. If you have, this is somehow a condition that you can check, and it's easier than checking that you map onto every image vector. Okay, so let me give you some applications of this idea. One of them we saw on the very first in-person day. Okay, so let's let Pn be the polynomials of degree less than or equal to n, and let x1 up through xn plus 1 be elements of R. Okay, then we get in a map from Pn, which is again of n plus 1 dimensional, okay, to Rn plus 1, so I've cooked it up so it's the same dimension, and the map just sends f to f of x1, f of x2, up through f of xn plus 1. Okay? What does this mean? Well, this is a linear map. Okay, so I'll call it T. It's a linear map, which is easy to check. All right? And you can see that it has no kernel. Okay, so the claim is that the kernel of T is equal to 0. Well, what would an element of the kernel be? Well, it would be a polynomial of degree n, where you plug it into, I should say these are distinct, n plus 1 elements. So you plug in n plus 1 different elements and you get 0. Okay, so in other words, such an element would be a polynomial of degree less than or equal to n, so that f has n plus 1 distinct roots. Okay, and that can't occur. All right, so you do need some work. I mean, you need to know that a polynomial can't have more than that many distinct roots. Once you have this, you get that the kernel is 0, therefore f is surjective, or T is surjective. Okay? So in other words, what this is saying is that for any choice, so for any choice of n plus 1 points in R, and any choice of values for those points, there is a polynomial which attains those values at those points. Those values at these points. Okay, so in other words, you pick, let me just do quadratics. You give me 3 x values, which can be whatever they want. Give me 3 real numbers that you want to attain, so maybe you want it to go through here, to go through here, and to go through here. Okay? And this fundamental theorem is saying that there's some quadratic, which passes through any of those points. Okay? So it might be, of course, it might be a line as well, right? If you chose, for example, 0 for all the values, then I would just produce the 0 polynomial. If you chose 3 points in a straight line, then my algorithm or this theorem would guarantee the existence of a line through them. In general, you get a quadratic. Okay, so let me give you one more kind of similar application. All right, again, something with polynomials. So we can take polynomials, again, of degree less than or equal to n. This will have a little more calculus in them. So we can take any interval, and let's say we have to, again, take n plus 1 intervals in R. 2, I3, and so on. Okay? So you fix n plus 1 number of intervals, and then what you want is a polynomial, okay, where the integral over I sub j of f attains any desired value, okay, for all j. Value for all j. Okay, so in other words, you give me, if this is a quadratic, you give me 3 numbers, okay? A, B, C, I want a quadratic which integrates over the first interval to be A, the second interval to be B, the third interval to be C, okay? How do you find that? Well, again, you use the fact that f goes to the integral over the first interval, the integral over the second integral, up through the integral to the in plus 1 f, is a linear map from Pn to R. Okay? Oh, sorry, R to the n plus 1. All right, what does this mean? Well, again, we're going to claim that the kernel of f is 0. All right, so why is this? Well, if not, then f integrates to 0 over all intervals. Okay? What this means, well, is that the area under the curve is 0. So in particular, you have to have a negative region and a positive region. They have to cancel each other out, but this can only occur if you have a 0 value. Okay, so therefore, f has a root in this interval. And again, this is a contradiction unless f is 0, since now we have n plus 1 roots. So contradiction unless f is 0. Okay? Again, we're going from subspaces of the same dimension. We have an injective map. We get that this is therefore surjective, and this is, what this implies is therefore for any real collection of real numbers, R1 up through Rn plus 1, there is some f so that the integral of f over this jth interval is exactly R sub j. Okay? Again, f might not have degree equal to n. It might be less, but you still are guaranteed this. Okay, so let me just end with a weird fact from topology. Okay. Which maybe makes this rank nullity theorem seem more surprising, or at least nicer. Okay. So in general, you can't conclude anything like the rank nullity theorem for arbitrary functions. Okay, so this is due to Piano in around 1900. You can look up Piano curve on Wikipedia. So there is a continuous, and I know I haven't defined anything like that, but there's a continuous map from the interval to the square, which is surjective. Okay, so this is usually called a space-filling curve. And actually, you can replace the word 2 with n. That's totally legit. And any cube, so here's the picture. You have a map here. It goes on to the square, and it fills up everything. Okay, so everything in the image so everything in the range is in the image of some map. Okay, which I think is pretty surprising. So this function is kind of impossible to describe explicitly, but I can give you some sort of picture. This is due to Hilbert, actually, but you can, again, I think, find that on Wikipedia. So you do it as a limit of functions. So here's what you subdivide the square up into smaller squares. Your first function looks like this. Okay? Not very space filling. Okay? So your second one looks like this. So I mean, so you do 4 by 4. And now you take this picture, maybe I'll try a different color here. So you take a copy here, then you go over to a copy here, Then you go over to a copy here. And then you go over to a copy here. Okay? And you can imagine that you can write down explicitly what the algorithm looks like. I mean, the next picture is already impossible for me to draw. So again, you subdivide everything. And then you start, again, you're going to see 4 copies of this picture here. So, you do, you see, I'm already going to get confused on how you do it. Something like this. And then this continues off, okay? This is just another, example. So corollary, linear algebra is nice. I mean, this is just something where anytime, you should never, in general, for general functions, be able to say anything about the dimension of the map, or dimension of the image and dimension of the domain. Okay, just doesn't happen. All right, so I will stop there. Thanks.